Okay, so it's revision. Halogenation of hydrocarbons, that's well known. Yeah. Fine. So it's SN2 because F minus is a strong nucleophile. It's charged basically. Anything that's not charged is basically a weak nucleophile. So it's not going to be SN1, it's going to be SN2. So AgX, when it's not AgF, which is AgCl, AgBr, AgI, these are insoluble, or I should say less soluble. And similarly Kx is less soluble in acetone. Ki is fine. So you might be thinking that why is that? Why is Ki like more soluble? Because iodine, it's larger. It has a bigger electron cloud to be polarized. So the bond is going to be more covalent, and that's why it can mix well in a not so much as a non-polar, but it's not protic. So yeah, it mixes well in that. ZnCl2 Lucas catalyst. Cool. Fine. px5, no big deal. Yeah, these are all just fluorinating agents. That's well known. Fine. Geminal dihalide from aldehyde with px5. Mechanism is straightforward, nothing bad. This reaction is not so extraordinary, it's just decarboxylation. So probably we are going to heat it, and that's why this will happen. Yeah, fine. Haloform formation. Yeah, basically the normal haloform reaction. This is very obvious. This thing also happens with NO2. You can do enolization, so then it can add X2 as well, right? So it's like HNO3, but instead of oxygen you have carbon. Okay, cool. So it does that. Not bad. Okay, next. This reaction it's looking good. Yeah. So yeah, you basically transport this from there to there. Fine. So the oxidation. Okay, so you need this thing R1SOR2 plus acid halide. Yeah. Okay, and then you create this intermediate species that reacts. Okay, complicated mechanism, but it's the same thing, right? Yeah, so it's just oxidation basically. Fine. So wherever we have like DMSO or things like these are probably just oxidizing agents. So cool. This mechanism, it's yeah, so this is like phosgene or something, right? I think it was like that. Okay, whatever, I don't remember its name. Words reaction, it's very usual. So yeah, next thing. Fine. Carbene formation, not bad. Oh, this is weird. So isn't this something like carbylamine? Yeah, so instead of saying this carbene, right, so we're not directly adding carbene over here. What we are doing is that we are starting with a halo form and adding a good base into it, and also having this amine over there, and that will do this carbylamine test, basically, right? Okay, cool. Fine. So that's okay. By the way, these 5-membered aromatic rings are actually like more reactive than the 6-membered ones. So I would expect this to go good, but yeah, it's still weird. Okay, fine. So it doesn't do a hydrogen shift over there, instead it expands the ring. Something similar happens with chromate, right? Yeah, the chromate and that also does kind of a similar thing. Okay, this nomenclature. So alkylidene, that's geminal dihalide. So whenever you have this lide thing, yeah, that's for halide or something like that. And vicinal dihalide, that is alkyline dihalide. So it's like more like alkene dihalide. So alkene plus dihalogen gives alkene dihalide. Very obvious. CH2X2, it's an exception, it's called methylene halide, even though technically it should be called methylidene halide, but yeah, fine. So that's aryl and alkyl halides. Hydrocarbons next. Okay, alkanes, these physical properties are useless, so you don't need to know all this. Alkanes are well, all hydrocarbons are colorless generally. Okay, hydrogenation of alkenes and alkynes, fine. Yeah, this thing. So the usual reduction, yeah, not bad. So it could also be that it like say you add Mg into this, then it will form RMgX. So that could be used. I mean, you could add water into that thing, and that will give you an alkane, but you can also use it as a reagent itself, so it can be used as Grignard. So you need some kind of Ha molecule to give you that hydrogen. So it could be alcohol, it could be water, it could be acid, I mean organic acid, or actually a mineral acid. Fine. Words reaction. Okay, cool. So used for symmetrical alkane creation stuff, right? If there are more than one reactants, more than one Rx things, then there's going to be even more complex kind of molecules, right? So cross products and maybe some alkenes, like disproportionation products basically. Okay, you can use hydride donors. Yeah, so hydride donors are nucleophilic, hydride donors that are nucleophilic, you can use this. Don't use things like BH3 or ALH3 or something like that, that won't work. Okay, fine. Use carbon ion donors to kick out X minus. Alright, so this is weird because I just said that you should not use electrophilic reagents, but yeah, so the thing is it's not exactly correct, because you can use electrophilic reagent. So Grignard reagent is something like an electrophilic reagent that can be used to do it. So it's not like you cannot use it, you can, but then it's not a hydride donor, it's now a carbon ion donor over there, right? Clemenson reduction. So by the way, this mechanism is like, I don't know if it's correct or not, but previously when I searched I didn't find the mechanism, but now I did, and this is the new thing that I have right now. So as you can see, it will only kill that double bond O thing, it won't harm anything else. So say you put an aldehyde into it, it will convert it not into something like an alcohol or something like that. No, it will just convert it to normal alkane. Yeah, So that's what it does. And it cannot use COOH group because of steric factors, and because it also does resonance and stuff like that. Yeah, reduction of ROH, these things with HI red phosphorus. So HI red phosphorus, it's a good reducing reagent. So red phosphorus, I told that it regenerates HI from I2. Well, the main reason is that it absorbs I2 basically. So yeah, like phosphorus plus I2, that gives us Pi3. That's why we have this over there. Similarly, like iron plus chlorine, that gives us FeCl3 and stuff like that. That's what we are doing. So HI is a good reducing agent. You know that iodination, both free radical and the usual thing for alkenes and stuff. Yeah, for alkenes also it's like reversible or something. And for alkanes, free radical iodination is reversible. So that's an important thing. So basically what will happen is that I minus will attack in SN2 everywhere. And then after that, you have this thing. This carbon iodine bond breaking. So just taking an example of Ri over there, Ri will break into R radical and I radical, and then that R radical will take hydrogen from Hi, and yeah, the chain reaction will keep on going. So this I2 gets attached to phosphorus. I radical could also like get attached to phosphorus directly, but yeah, fine. So that happens. Since I2 is irreversibly consumed to create Hi, thus equilibrium is shifted to right and we get an irreversible reaction total. Yeah, so that's about right. Soda lime decarboxylation, pretty well known, I don't need to do it. Called base electrolytic decarboxylation. Fine. Yeah, that's also pretty well known. So you can directly use a salt, or you could first create that salt with acid base reactions. Okay, hydrolysis of carbides, fine, well known. Halogenation, free radical halogenation. So yeah, this is important, ratios for amount of product formed. So if you have all 1 degree, 2 degree, 3 degree kind of substituents over there in the reaction mixture, so fluorine will majorly go for the 1 degree substituents because more hydrogen, so more probability of fluorine striking is the right way to do it, right? So it always has, generally it has a high activation energy for that kind of process. It has a high energy. Fluorine atoms have high energy for that kind of process. Its activation energy is lower, basically. That's what I should have said. Okay, and chlorine, it is more selective. It goes to 3 degree the most, and the ratio is still, it's okay, it's not that bad or anything. But then for bromine, it just like explodes. So 1, then suddenly 82, then suddenly 1600. Okay, so that's big. And iodine, it's a reversible reaction, as I just told you, and it doesn't form 1 degree, 2 degree that much. 3 degree it might form, but then once again reversible reaction. Inhibitors like O2 decrease rate by forming undesired relatively stable species like ROO radical. Okay, fine, that's all right. Nitrationsulfonation. So this is nitrationsulfonation of alkanes, which, yeah, it's not having any functional group that we can use to make these molecules attack on it, so it is essentially going to proceed by radical mechanism. And yeah, I don't know what the mechanism is though, but it does that. Cool. This happens because SNO3, these are yeah, you could say so, but whatever. SO3 plus SO4 is called oleum. So, well, people say that it's a mixture, it's not exactly a molecule in itself. Well, yeah, that's partly correct that it's a mixture and not necessarily a completely new molecule. It's not a specific ratio that you need to put SO3 and H2SO4 in to get a specific molecule. No, it's kind of an equilibrium process going on over this. So there is this molecule, but majorly it's just a mixture. So it's called disulfuric acid or pyrosulfuric acid. Fine. This oxidation, it works with KMnO4 and some other oxidizing agents. It might work with say peroxide, yeah, like that can do it, I guess. Okay, right, obviously peroxide would work because yeah, the radical stability is almost similar to carbocation stability. So this will work for the 3-degree alkanes. Combustion, once again a radical mechanism, basically this thing but with a lot more oxidizing power and yeah, and heat. Isomerization. So I've written that AnCl3 is used to consume Cl- as well. That's only part of the reason. It's also used to attack this alkene, so it too can create this positive charge and stuff and initiate the process basically. Alright, next, alkenes. That's a rule, hyperconjugation. Fine, we know all that stuff. Oh, this is actually some important stuff. So surface area trans is less than cis and close packing trans is more than cis. Fine. Partial halogenation of alkyne. So it's Lillard catalyst is used to decrease reactivity of H2 so that only alkyne will be reduced and not alkene and you know that stuff. Fine, but it gives a cis product. So if say we want trans or anti product, okay, that's better, anti hydrogenation, then you can use liquid NH3 plus some alkali metal. Yeah, so it creates this solvated electron thing that like has another like some stuff in inorganic chemistry that it gives ammonia a deep blue color because of electron transitions and stuff, whatever. So it basically does this thing. So these solvated electrons are like, yeah, you can just bombard the alkyne with these things. Okay, cool. And we know like alkyne is more reactive for this thing than alkene because sp hybridization, but it will turn to sp2 hybridization, but fine, we get the thing, right? Yeah. Dehalogenation. Oh, by the way, terminal alkynes won't do this because yeah, okay, this is not the correct reaction over there. It's not like, yeah, they are acidic, so this can happen, but okay, fine, I'll take that because the thing is basically there's a bit of sodamide going on so that is a very good base and it can just pluck out this thing. But yeah, this reaction also happens actually. Dehalogenation with zinc. Cool, that's fine. So notice there's no flipping over there, so zinc just inserts itself without any change in stereochemistry whatsoever, which is probably involving some kind of anion, carbon ion, and that's why it's still the same stereochemistry. If it involves say free radical or carbocation, it would be bad, so it must involve an anion. Fine, and then it does that. Cool. Elimination, E1 kind of thing. E1, yeah, it's E1, fine. Dehalogenation with I minus in E protect solvent. Actually, this is more like E1 CV. Whatever. Move on. So the first step I showed is that it does SN2. This may or may not be true, but in the end, it's like no change in stereochemistry and just like elimination basically. So it can form this thing I2 Yeah, iodine is really weird for some reason, because it can do these things which other halogen molecules cannot do that easily. Okay, dehydrohalogenation. Yeah, that's well known. So in case this whatever this thing is, N plus CH3 thrice, if this group is the leaving group, then you will get the less substituted alkene to be the major product, because it's the Hoffman product. Yeah, notice this reaction will in fact be kind of irreversible at the start, at least. So that means whichever one has less activation energy, that one will be the major reaction. So yeah, that's what will happen. Fine. Dehydration of alcohol even after protonation of OH to this guy. Sure. So P2O5 and Al2O3, these are good desiccants, which means that these things can accept lone pairs, and then it can also accept that hydrogen stuff over there. So like basically it can dehydrate your molecule. H2SO4 is also something that can dehydrate a molecule, but like fine, that's not important over here. Okay, cool. Pyrolysis of esters with cyclic transition state, not important. Skip. Witting reaction, phosphoniumylide, it does this thing. Okay, both GI, fine. And this guy, isn't that complicated. Colby's electrolytic decarboxylation, that's fine. Dehydrogenation, sorry, hydrogen, not D. Okay, cool, this is fine. Addition of halogens, well-known mechanism. This halonium ion, or whatever it's called, yeah, that kind of preserves your stereochemistry, or at least gives a stereospecific product. I shouldn't say preserve or whatever. Okay, fine. Reaction with acids, yeah, alkenes, these just add acid through this mechanism. So if there's high concentration of A minus, then this species can react with the A minus that's roaming around. But if it's a low concentration, then it has to wait for a long time before it can react with it, and can better react with the solvent molecule that's just in the proximity of this guy. So yeah, that's exactly what happens. So instead of saying low concentration of A minus, it could also be that A minus is just so stable that it doesn't want to react. It's not a good nucleophile, that is, or a base. I mean, it's obviously not a good base, but it's not a good nucleophile as well. So say for example SO42 minus, yeah, it's not a good nucleophile. Fine. Okay, reaction with HX and HOOH. Okay, so in this case the stereochemistry is regio, fine. So the whole thing is in reverse. So HX adds the opposite way of what it should have been if this was just HX. Okay, cool. Allylic substitution, yeah. So I drew all this complicated mechanism, but it's pretty simple actually. It's just that you take this allylic hydrogen and kill it with some kind of radical, creating this species, and then this species reacts with something, say X2 molecule, or for this case YZ molecule, and then it steals something, creating this thing, and this chain reaction keeps on going. Okay, carbene addition. So this is a good thing you should know, that triplet carbenes, well, they have the electrons in different orbitals, so they need not be paired basically. So what can happen is that these electrons will be unpaired because of that maximum multiplicity rule, or whatever that thing is called. So what that means is that when it adds, it cannot add right away by donating a lone pair or accepting a lone pair. No, it needs to do it as a radical basically. So it first uses one of the electrons in one of the orbitals to form one bond, and then forms the other bond over there. And also it cannot form the other bond right away because these radical electrons okay, where was I? Fine. So these radicals, these are not of opposite spin, so we need to make them opposite spin, and needs that needs time basically. So if we wait for long, then this can convert to opposite spin, and then this will happen. Okay, cool. So epoxidation, MCPBA is not specifically what we should always use. It could be any peroxy acid, it will always work. But yeah, so it's the popular reagent that we use. Okay, cool. So you might say, why peroxy acid? Because that radical over there, that must be stabilized. If it's not an acid, if it's something else, well, it's not stabilized. So yeah, you need this acid group for this kind of mechanism to happen. It's concerted and whatever, you know it, right? Okay, this reaction is epoxides. Fine. So epoxides, they are not so stable in protic solvents because they can go through solvolysis and create these kind of vicinal diols. Cool. Addition of alkane. This mechanism is not really useful as such because it does create a new species and it can be done, but then there's so much more that could happen. There's like polymerization and some other stuff going on over there and rearrangements, and let's just skip this. It won't be asked, I guess. Isomerization is an important thing that will be asked most times. Okay, H plus catalyzed polymerization. Fine, it's a straightforward mechanism, except it's not so straightforward. It does not necessarily form a chain of n units or n plus 1 units or whatever. Instead, in different condition, it forms different lengths of chains. So say for example, in order to get low density polythene, what you actually need to have is that the intermolecular forces should be low. So for that, the molecules themselves should be smaller, so less surface area and all that stuff. So how do you make molecules, the chains basically smaller? Well, you increase their reactivity, so there are more chain reactions going on, and that means there are more chances for the reactions to terminate as well. So the terminations what I'm telling is, the terminations, if they happen faster, the chains produced will be of less length. I mean, that's obvious, right? Because there's like so much of small chain radicals roaming around that termination will happen at a good rate, and that means you will have very small chains. Instead, if it's very slow, then there's only like 1, 2 or 3 chains. I mean, okay, I'm exaggerating, it might not be like that, but there's like small amount of chains in that mixture, but these chains are continuously increasing in length, so it will take a lot of time before these can terminate and find radicals. Okay, why did I say all that? Next, oxymercuration, demercuration. So yeah, this thing, and then demercuration mechanism is not really that important because you just need to know that there's this hydride ion that's required, and it's basically NaBH4 that's used in demercuration step, and this does this thing. Fine. Okay, cool. Actually, this might not be a radical over there, right? This kind of like Yeah, it is not necessarily a radical over there. I think it should be a carbon ion over there. Yeah, and a G plus. That will be better, isn't it? And that will create this thing. Okay, whatever. Next, hydroboration. It's a concerted step, and it forms this thing. So BH3 is very reactive. It does not exist like simple BH3. Instead, it exists like this, B2H6. It's like similarly, uh, what was I going to say is like what was I going to say? Okay, BCl2, or it was like BCl3. Fine. One of them also exists as a dimer in gas and as a kind of weird covalent bonded structure in solid state. Oh, it should be beryllium. It shouldn't be boron, but I guess boron also does something like that. At least aluminium does. So whatever. Hydroboration oxidation. So yeah, mechanism is really nice. It's easy to follow, but not so much useful. Basic key points are that in hydroboration oxidation, you are going through a single concerted step. In hydroboration, you're going through a single concerted step. So wherever you have this kind of negative charge develop, that's where your boron will add, basically, right? So wherever it can like it has that extra charge density, and for the I should say, like, yeah, that's what should be happening, isn't it? That looks about right. Yeah. So did I just mess up the specificity? Well, in a normal acid addition, what happens is that first H goes, so wherever there's like a lot of electron density, your hydrogen will be attached. So yeah, it's the opposite of what happens in normal reactions, which means it's good, because that's what we're looking for, isn't it? Yeah, that's right. Okay, so once that's out of the way, you can just oxidize this by doing this thing, and that will work. There's also BH3 reduction. So you might say, why not hydroboration reduction? Well, there exists something like that, but it's not for alkenes. It's for things that can donate lone pairs. So alcohols, acids, aldehydes, things like that. Not for alkenes exactly. Okay, cool. Next, Diel-Alders reaction. Okay, that's fine. Ozonolysis, that's important. Ozonolysis is really important. Yeah, so this ozonide, in alkene ozonide, it's like very stable. For alkyne ozonide, it's unstable, and it does not need anything to like react with in order to open. For alkyne ozonide, basically, this ozonide does need something to react and open with. So in radical mechanism, or I should say oxidative ozonolysis, it reacts with OH radicals and produces this thing. Well, if this were like, if one of these was an aldehyde, then the HO radicals, sorry, not HO radicals, the peroxide that will convert the aldehyde into an acid, basically, right? Okay, that's cool. Yeah, and then for zinc, this will be reductive ozonolysis in that case. Cool. So it just creates ketones, aldehydes, things like that. And if there's like excess of zinc over there, it might create alcohols. It does create alcohols. And then there could be Lewis acids. Well, these don't exactly work for creating ketones and stuff, but if there's hydrogen over there, these can do this thing. Okay, cool. So it's like, look at the mechanism. that negative pushes that away, then this pushes that away, and yeah, you got this negative charge over there. Cool. I mean, the negative charge cancels the positive charge over there. Cool. So that's nice. Yeah. So it creates this acid thing, at least something that looks like an acid, and this ketone or aldehyde thing. Okay. Hydride, fine. Yeah. So it creates OH minus. Okay, it's all right, and we totally expected it because it's a reducing agent, right? Okay, and yeah, so basically because it's a reducing agent, these whatever these things are, these will get converted to alcohols most likely. Okay, H2, fine. Okay, that's fine. This is not bad. So hot acidified KMnO4 does a similar thing as ozonolysis. In case H is there, this does that, and then further oxidizes to acids. But cold alkaline KMnO4 creates these diols over there. So yeah, fine. And NHSO3 is used to reduce the remaining oxidizing agent. It's not always involved in the mechanism. Extended oxidation. So you don't need, okay, you should not have 3-degree alcohol. I wonder why, but fine if they say so. So when it's not a 3-degree alcohol, okay, obviously not a 3-degree alcohol, because you need to create this aldehyde thing or ketone thing or whatever this is. Then aldehyde to acid. Okay, not bad. Fine. Woodward hydroxylation. So we already saw this thing over there. It should be OI, covalent bond, not an ionic bond, but you get it, right? So we already saw this kind of bond. Yeah, so we know these are weak and these break. So like it acts as I2 or IX for that matter, and it basically does this thing. And then there's SN2 over there, it does that, then that. Fine, kind of complicated. So stereochemistry, that will be given by the complete mechanism over there. But Woodward hydroxylation is particularly thin. There's also an reversed hydroxylation, which is anti, which happens when there's so much of these carboxylate ions that they start doing SN2 on these intermediates that you have. Okay, so this intermediate does not like do solubilisis over there. Instead it goes with SN2. So this is the mechanism for solubilisis. That's not even important. Okay, KOH as H2O, right? So this is not, this OH minus is not doing SN2 over there. No, it's instead it's doing SNAC, so acyl nucleophilic substitution stuff with this carbonyl. Cool. So yeah, this mechanism, N2H4 plus H2O2. Weird. That's all I can say right now. Okay, so it's not problematic because N2H4, this can definitely get oxidized to this thing, right? Yeah, cool. And then it can do that. So So remember N2 is a gas, so it can do this thing. Okay, next, Rayleigh reaction or relay reaction or relay oxidation or whatever this thing is. Okay, so SeO2. Huh, complicated. Isn't that weird? I mean, I get it. The mechanism is understandable, but why is this happening? Whatever. So first you form this thing and then do this thing. How did you even do that thing though? Probably with a hydrogen shift over there. Oh, okay, wait. Why even do that? Just to rotate the whole thing. Yeah, just rotate about this sigma bond over there. And then break the pi bond like that. And then show it attacking like that. And from this guy, okay, that's fine. And then what? Then it does hydrolysis. So selenium, as we just saw, it can form 3 bonds over there, or actually 4 bonds or stuff like that. So it will form 3 bonds. It will first coordinate with oxygen, and then you got a negative charge over there, which you can use to basically separate this thing from there, and then this oxygen will lose its H plus to that alkoxide over there and create this guy. Cool. Well, it can act as an acid if there's an hydrogen attached to it. So it only acts as an acid if it's terminal. Dehydrohalogenation of alkenes. Doubtful mechanism, but the only mechanism that you have. So yeah, this could happen, or it could just be, even CP or something similar to that. But in either way, you have similar kind of stereochemistry and all that stuff. So it's not bad at all. And yeah, that negative charge over there, it's not delocalizable. Fine. Dehalogenation of alkene. Okay, the usual thing, insertion of zinc into this guy and then heating it to remove all that stuff, creating this. Oh, by the way, C2H2 is a gas. It's not a solid or liquid or anything. Yeah. Alkylation of terminal alkyne. Huh. Yeah, fine. Kolbe's electrolysis for this one as well. Okay, cool. So I believe this should be some kind of concerted step, because sp2 radical, that's not a good thing, right? So fine, it should be like a concerted step. The main thing is that CO2 is irreversibly removed in the atmosphere. That will boost the reaction forward. Hydrolysis of carbides. Okay, cool. This electric arc method is also used to create fullerenes. Yeah. And next question, next whatever the thing is, its reactions: halogenation and dehydrogenation, we already got that. Synhydrogenation, addition of acid, yeah. Hydration. Okay, so we get first of all enol, and that enol will get converted to a ketone. Okay, hydroboration, same as alkene. All right, cool. Hydroboration, oxidation, same as alkene, except we get tautomized products. Fine. So reaction of terminal alkyne with carbonyl. Terminal alkyne with carbonyl. Okay, this thing. Yeah, it's not complicated at all. it definitely can happen. It's just nucleophilic addition on acyl or carbonyl group. Not acyl, right? Acyl is different. Whatever. Oxidation to diketone. By the way, there's like two different things that could happen. It could convert it to a diketone, or it could convert it into an acid, actually two acids. So yeah, and Wikipedia states precisely that the mechanism is not well known. That's a problematic thing. So yeah, so this may or may not be correct to say it converts it into diketone, but fine. So it's with acidified or hot cheminophore. Huh. And with cold cheminophore, uh, you have this thing, a diol, something. And yeah, it will just tautomerize right away, creating a ketone. Okay, cool. Ozonolysis. Right, so as I told you, this ozonide is unstable and this will break directly just when you put water into it, or actually don't even put water, it will just break away. Okay. And it creates this acid. And here too, there's actually two different products that could happen. That it could give you a diketone, or it could give you this anhydride thing, right? So if you are using say water on it, it might give you that thing. If you're using ozone as a gas on this thing, maybe it will give you just anhydride. Who knows? Cyclic polymerization. Yeah, it's well known. So you need a hot ion tube or some kind of hot surface on which this can stick. That will give you this reaction. Diamine hydrogenation, same as in alkene. Okay, next. Aromatic hydrocarbons. This mechanism is known. Orthopara directors for EAS in benzene. I know all this stuff. Deactivating power order. Okay, this is a rough order, not to be taken seriously. Different aromatic systems. I know the stuff that whichever has more resonance structures, well, that wins. So whenever you have these so-called aromatic systems preserved, right, when you are doing this naively, where you're creating the resonance structure naively, remember aromatic structures can exist in two different structures actually. So it's not just one structure, two structures, and that's why their contributions are amplified. So there's like more number of resonance structures over there basically. So let's try to preserve that aromaticity. And by the way, naphthalene, it can give you say uh, two aromatic substances, two benzene rings. It can give you like more stability basically. All right. Okay, cool. Yeah, that's okay. This is well known as well. So if you have a destabilizing group on one of the rings, the electrophile or nucleophile, it will attack the other ring exclusively. Okay, cool. That's all right. If there's resonance, it's good. If there's not resonance, not good. That's obvious. Pyrene is less reactive than benzene. Yeah. So this effect that positive charge on nitrogen is more destabilizing than carbon, it's actually not that correct, because carbon and nitrogen, yeah, like we can say that the negative charge is not exactly on the nitrogen, because first of all the resonance structures as we draw them don't exactly exist, right? They are hypothetical. We think that those exist and stuff, but really it's the final thing that you have, the final hybrid that exists. Similarly, quinoline and isoquinoline are less reactive than benzene. Okay, fine. So, for a positive charge, if you attack over there, you will have more cases where you have an benzene ring over there, right? A preserved benzene ring. I shouldn't say benzene at all because you got this nitrogen over there. So yeah, whatever. The pyridine ring, fine. Yeah, and this dot thing, it puts a positive charge on nitrogen, so it's like a little more destabilizing than this star thing over there, because it too puts oh sorry, this dot thing doesn't put a positive charge on nitrogen, and this star thing does. That's why star thing is more destabilizing than dot thing, so it's lower in that order. Similar kind of thing happens over there, so you can see the order is reversed now. Okay, different types of E plus. Okay, sulfonation, it's a reversible thing. You can use either oleum SO3 mix and H2SO4, or you could just use H2SO4 directly. H2SO4 is generally used to give you a good H plus concentration, but it can also be used as a nucleophile or an electrophile. Okay, cool. So polysubstitution doesn't occur. It's used as a good blocking reagent because it's like bulky and it has affinity for para position, and it will attach over there, and then you can do some other stuff that will put things on ortho position. So yeah, it's good. Nitration, fine. So just HNO3 plus a lot of H plus concentration, which is probably from H2SO4. Yeah, you could also halogenate this thing, for which you need a Lewis acid catalyst, but I would say don't do it with phenols and stuff, because the problem is that those coordinate to the Lewis acid catalyst, and yeah, actually that's in the in a section over here as well, so we'll skip that talk for later. HOX can also be used. Okay, fine. Okay, the catalyst is necessary as aromatic systems don't react. You will see that this is not exactly correct, because there are aromatic systems that react with it directly. Iodination also needs an oxidizing agent to destroy that. That is an important thing, that HI is a good reducing agent, so we don't want it lying around. We need to destroy it right away. Or you could just simply use something like ICL, Friedel-Crafts alkylation. Yeah, so for aluminium, rearrangements occur at room temperature, but if you heat that thing, the reaction mixture, then these rearrangements occur even if it's not just aluminum, it could be anything, right? And rearrangements will still occur. So if the cation can rearrange, it will rearrange, believe me. So this bond over there, it's like very polar but not exactly ionic. Shit. Yeah, and that's why it can allow rearrangements. Okay, so instead of using a Lewis acid catalyst like that, you could also use these things. ROH plus H plus, that gives us R plus basically. Strained ring plus Lewis acid. Alkene plus H plus. Okay. Epoxide plus H plus. Negative R is an activating group, so polysubstitution occurs even when R plus is a limiting reagent. To decrease this, we can take large concentration of aromatic substrate. Okay, that's fine, not bad. Anhydrides can be used. These whatever these things are, these can also be used. Isn't that weird? Okay, so amides can also be used. Okay, but this looks like it's giving two different reactions. So, yeah. By the way, this thing is actually kind of unstable, because you got these oxygen lone pairs and nitrogen lone pairs roaming around. It's not good. COR is deactivating, so polysubstitution doesn't occur. Okay, cool. So it's not at an ortho position generally. Well, okay, I said that COR is not bulky, but it actually is also bulky at the same time. So, yeah, both are the reasons. Fine. Then you got this reaction. Okay. Those are a lot of different things occurring over there. I'm not going to sky. That's weird. Okay, it's not that bad. Fine. Oh, now it's getting bad. So this is like cyanide. Okay, fine. That's okay. Cool. We said that it's absorbed by MXN, but then won't MXN first of all directly coordinate with cyanide with? Well, I guess it just helps it in doing stuff in that case because it's creating positive charge on nitrogen. So yeah, that's something. So either it is helping in doing so, or it is still helping in doing that by absorbing chlorine. Fine. Okay. Cool. It can do that. Not bad, not bad. So phenol has all of these different reactions, which is shows. This is just one of them. Okay, cool. And then this guy can do Fry's rearrangement, so that will create a different thing. Yeah, whatever. And what is this guy? That's weird. Oh, wait, I've seen this kind of thing somewhere. I don't remember where, but so OPX3, it's generally used for halogenation of acids basically, but over here we are using an amide. Let's see what it does. So it looks like it's not doing anything. Fine. Wait. Where did that OH group go? Okay, so it did kick out something. It halogenated, sure, but oh, okay. Wait a second. Yeah, it couldn't make that R1 R2 plus leave, so instead it had to just become a carbocation and add to the aromatic system like that. Okay, HGOR. Diazonium salt, very useful. Yeah, everyone knows this mechanism already, I guess. S2O8. This is something that I always forget. Okay. Okay, fine. The usual, basically. Okay, then do that and create this thing. Not that bad. Huh. Yeah, definitely it's not bad. Then okay, fine. Reaction with AROH, AR, NH2, etc. I should just see reaction with phenol or aniline, etc. So aromatic substitutions. Okay. So aniline and phenol don't react when there's Lewis acid catalyst, because it coordinates with that and decreases the concentration of catalyst, so making the reaction very slow. By the way, if there's like you for some reason, well, yeah, so if you put a lot of catalyst, even more than the phenol content, then what could happen is Fry's rearrangement. Okay, so that could happen, or you could just basically first of all react on the oxygen, right, acylate on the oxygen or something like that, and then add the catalyst. That will also work. Okay. Yeah, these reactions are known. Raymer-Tayman kind of reaction. Okay, fine. I know these. So it reacts with X2 without any catalyst. So adding HNO2 in HNO3 for nitration of phenol, it in fact for other aromatic substituents, for other aromatic reactions, it slows down the reaction because it consumes the H plus that is required for HNO2, right? So sorry, for HNO3 to convert into the electrophile that we want, which is NO. No, NO2 plus. Yeah, NO2 plus. Over here, what would happen is that it would just like take the H plus and convert to NO plus. So generally, it will slow down the reaction. But for phenol and stuff like these, what will happen is that NO plus will also be a good electrophile. So you basically need a really good electrophile to add on a aromatic ring. NO2 plus is a very good nucleophile. electrophile, so it can add on ring directly. NO plus cannot, but NO plus can add on aromatic systems with these things over there, phenol kind of thing or aniline. So because it can add like that, it will first add and then it will get oxidized to NO2. So this is basically Fry's rearrangement over here. So yeah, these are fine. This reaction is fine. Phenol from benzoyl sulfonic acid. Yeah, it's fine. Send me a reaction. Shouldn't be that hard to remember. Enzyme mechanism. Yes, this thing. I forgot when it was used though. Yeah, whatever. Oxidation. Alright. There's like some kind of I don't remember its name. What was it? CrO3. Yeah, that was the thing. It was something that could oxidize our hydrogen on the benzylic position to an alcohol and then to an aldehyde. So that was one thing. But how do you cut off carbon-carbon bond? Well, that's still a mystery to me till now. Yeah, I'll find it out sometime soon. Base catalyzed desulfonation. Yeah, sure. So this thing, I don't think this is exactly correct, because if there's base roaming around, shouldn't it just do AISN and create phenol over there? I guess both reactions happen. So I don't know, phenyl was so easy to leave. Okay, next. This is going to be a big one. Okay, all of these mechanisms are just not needed. Nucleophilic addition, acid catalyzed. Fine. All reversible reaction. Yeah, thioamines of dehydration reactions. Okay, cool. Acidity of carbonyls. We know this stuff. Yeah, so phenyl and alkyl groups, these are still electron withdrawing, so these basically increase acidity even though they do resonance. Sorry, alkene group, right? Yeah, whatever. So these are still electron withdrawing and increase acidity even though they do resonance, and we predicted that these should decrease acidity. But yeah, these kind of things happen, whatever. So only tertiary alkanes can be converted to ROH. KMnO4H plus heat, so hot KMnO4 basically. Fine. 2H plus OH minus gives this guy. These mechanisms are okay, we can do it. This is just normal acid addition. Oxymercuration, demercuration, we know this. Yeah, so instead of BH3 we can also use Si2BH, dicymetborane, or NBBN. Fine. So diborane is a more like an inorganic reagent, so it's, I don't know, maybe it's more expensive or something, I don't know, really just I don't know. So we use these two weird things instead. Okay, ozonolysis. Okay, that's cool. Mild oxidation. So we just saw this mechanism for Woodward hydroxylation. So if there's no H2O over there and there's excess of RCO minus over there, then this will happen. It's Prevost dihydroxylation, right? So it's just in different stereochemistry, nothing else changed. So it's anti hydroxylation. Okay, then epoxide, and that epoxide can be hydrolyzed to give anti products. Okay, cool. Fine, diazonium salt, and that diazonium salt can be hydrolyzed as well. So that will give us an alcohol. So much to just create an alcohol. That's like, why? Fine. Prince reaction, not in syllabus, I guess. So yeah, skip that. But the main thing is that you can use formaldehyde on alkene to form weird products. All these weird products. Okay, catalytic hydrogenation of carbonyls. SOX2. Okay, cool. Okay, fine. So RCOH can't be hydrogenated like that, not with catalytic hydrogenation, at least not at a practical rate. So instead we convert it to something else and then do it. Similarly, these cannot just be reduced by ALH. So instead we convert them to esters, which can be reduced by ALH, right? Okay. So as I told you, Grignards are electrophilic, and these do this thing. So they don't act as base right away. If the hydrogen is in proximity, like it attaches itself to an alcohol moiety, and then it can do it. Then it can act as a base, because at R minus it wants to combine with something. It can also combine with hydrogen, which is already now having some kind of positive charge roaming around. So yeah, it can act like that, or it can act like this. And that's why you need like extra Grignard to actually, convert acid into something like, well, whatever it converts to, like aldehyde. I don't know, it converts to something, right? Reduction of metal and acid, that's the usual reduction we have seen till now. Okay, univalent metal. Okay, fine. And then for bivalent metal, this thing happens. Marvin-Pondroff-Verlet reduction. So this is more like a disproportionation reaction. So you or a redox reaction, I don't know. So you oxidize a given ketone or aldehyde or whatever. Not an aldehyde, I guess. It's ketone. Fine. Sorry, you reduce a given ketone, but in that process you oxidize some ketone that you have excess of. So say you want to create a particular ketone for something, and then you have some other ketone that is available to you, right? So like commercially or something like that, then you can use this to save time and create this precious ketone that you want at the cost of something else. Yeah, that's fine. And next you have amide or alcohol plus ALH4. So it needs like 3 moles of AlH4 to actually get reduced, because first of all it acts to give H2 gas, which is basically a wastage of the AlH4, and then it reacts with it actually. Yeah, and AlH4 is very precious, so we don't use it. Instead we convert to ester, which cannot act like this and do this. Yeah, waste our AlH4 by creating H2 gas. Cyanide plus AlH4, straight away it's a very straightforward mechanism. Okay, cool. So depending on how many equivalents of H4 you are going to add, it will do different things. Wait, what? Okay, this is just one AlH4 that was required. Oh, okay. Depending on the number of equivalents of dibal H added, it can do different things. That's better. So dibal H is, wait, doesn't dibal H not reduce cyanide or something? Fine. I don't know much about that. Okay, this is weird. The 17 reaction doesn't seem bad. Okay, BH3 reduction of acid, a very long mechanism, but the final thing is that it reduces to an alcohol. Okay. Let's look at the number of equivalents required for BH3. So you need 1, 2, 3. Till now you got 3 equivalents. Okay. Wait a second, where did that one go? Okay, over here. So you need 3 equivalents. Yeah, you exactly need 3 equivalents. Fine. Okay, next. That's weird. So if there's HX over there, so X minus is a good nucleophile relative to SO42 minus. So if it's HX over there, it will create this thing. If it's H2SO4, it will create this thing. Okay, cool. And if it's a low concentration and heated environment, then it will just create alkene. Yeah, that's like obvious. Cool. Yeah, this mechanism is alright. So you can use X2 to reduce, to oxidize any alcohol. Well, I've only seen it with iodo, right? We know that iodine can be used to do this directly. Yeah. What was it once again? Oh yeah, it was the iodo formation. So it just oxidizes the alcohol right away. And other halogens don't do it that easily actually. So when I write X2 over there, I should really mean I2, but it's like whatever. Maybe others also do it. I don't know. Copper chip oxidation. It's alright. 3 degree gives alkene. Hydrogenation of acid halide or acyl halide. I'm not surprised by this thing. So it uses Ron's-Mend's catalyst to decrease reactivity. Oxidative ozonolysis, fine with peroxide. Yeah. Oxymercuration, demercuration of alkynes. Stefan reaction, something else. Okay, SnCl2. So tin, it goes from being +2 to being +4. So in this case, it's a reduction basically. So you're going from carbon +3 to carbon +2. Yeah, it's a reduction. Okay, cool. The mechanism is weird. So it goes by single electron transfers. That's fine, not bad. And then there's like an E1 step over there or something like that. Oh, I never thought about it like that. Diol to so geminal diol to ketone could be through an E1 kind of step or E2 kind of step. It could be, right? Yeah, there is possibility like that. Okay, next. So ALHI-Bu2 isobutyl 2, that's diabal H, and it converts. It does convert cyanide into this thing. So depending on the number of, so as we saw, ALH just straight away converts this thing to an amine, but diabal H, depending on the number of equivalents that you put in, if it's just one equivalent, then it converts it into what is this thing? Yeah, into first an imine or imine or whatever this was, and then when you hydrolyze it just gives you aldehyde or ketone or whatever. Itard reaction. Yeah, this is benzylic oxidation basically. So like benzylic oxidation, not so hard to understand because you got a lot of pi bonds around here and you can use that to oxidize stuff. Still, it's amazing that you oxidize something that didn't have an OH already existing over there. I get it, it's an alkene kind of thing, so you can do it, but you didn't do it on the alkene. No, instead you did it somewhere near to it. What am I talking about? It can be done, of course it can be done. I'm just like not sure about why benzylic oxidation removes alkyl substituents over there. Should it happen or not? It does happen, of course, but why should it happen? Okay, whatever. CrO3, it also does the same thing. It forms aldehyde, just a little different mechanism. Okay. Okay, it's in one over there. Okay, fine, this is all right. Getterman Koch, basically Friedel-Crafts acylation. Just wait a second. Yeah, Getterman Koch, basically Friedel-Crafts acylation. Yeah, looks right. Okay, not bad. R2CD is also a carbon ion donor, so it only reduces acyl halide to ketones. Cool. So it cannot add to it directly. Instead, it needs something that it can take away first. Yeah, weird, isn't it? Whatever. RC triple bond cyanide plus Grignard. Not surprised that it gives ketones. Really. I mean, it does depend on the number of equivalents that you had. That basically tells you that what are you going to get. But I believe even if there were like two RMGX, it would still be just a ketone, right? Because how is it going to do that? Create two negative charge on nitrogen. Yeah, how does that even happen? Yeah, whatever. Next, hydrolysis of amide, cyanide, etc. Yeah, whatever. Ignite plus CO2. Okay, not bad. Now the main thing starts. Specific reactions. So cyclic acetal or chiral formation. A good example of this thing is when you got two OH groups, so just one vicinal diol with nothing else over there. That does it. That forms a 5-membered ring, which is basically used to, like, no, that's not used. Okay, dithiones are used to protect stuff. I don't know what that used is. What is like the purpose of doing that? Okay, fine. Next. Okay, cool. Cyanide. NaHSO3. It adds like that. Okay, cool. Ketones won't do this effectively, so maybe we can use this as a test. Who knows? Okay. Tolerance test. EGNO3 plus NaOH. Fine. So the main thing is that you just got Ag plus over there, and Ag OH actually like Ag OH, it doesn't exist really. So instead you have to use Ag2O solid and add it to NH3 to give you this thing. And then once again, like creating Ag2O, it's another problematic thing. So for that you used AgNO3 plus NaOH. And NO3, it's soluble to a good extent, so it doesn't precipitate or anything, but Ag2O does. So AgOH is not stable or anything, so it will precipitate as Ag2O, and that with NH3 forms this kind of complex. So yeah, that's cool. So Ag, it can be converted to Ag metal very easily, right? That's why we use it. Doesn't look too complicated over there. Ketones don't do this reaction. Why? I don't know. If I'm not getting a reason, then it must have been something very complicated, or I didn't find the reason in the first place. Okay, cool. What am I talking about? Obviously they won't. Okay, they won't do it because you need that hydrogen over there. It's in the mechanism itself. I can't just overlook the mechanism. It is important in these tests. Tolerance test and Felling's test mechanisms are very important. Okay, let's go to the mechanism. Start with single electron transfers and create this thing, and then OH minus. Okay, cool. This is something like a H radical shift. Okay, cool. So you notice what's happening over there? It's always just Ag plus coordinates to oxygen and then breaks away homolytically. That's the whole thing. That's all that happens. It doesn't coordinate to carbon whatsoever. So you saw that H radical shift over there. That's a very important part of that, because it basically tells us why ketones can do this, can't do this. Okay, Felin's test. So you are using Cu2 plus Cu2 plus citrate. So that molecule is soluble in water, while COOH twice is not. Okay, cool. Mechanism is not completely known, but this is the most possible path. So you need both these blue hydrogens over there. So I could draw this mechanism while sleeping. Yeah. So you see that this changed, basically like this very unstable situation suddenly changed to a very stable situation. Well, this same thing is also in pinnacle rearrangement. So yeah, that's also something that can happen. Hydrogens marked in blue are necessary for this reaction. Ketone can't do this. Okay, cool. Halogenations of alpha hydrogen containing carbonyls. Yeah, this reaction is not bad. I know this one. I've used this a lot, so not bad. I mean, when I say I've used this a lot, I've drawn this a lot of times while uh, doing other mechanisms. So yeah, haloform formation basically. That's where I use this a lot. Okay, cool. So haloform formation, it's all right. Then you got aldol addition, and this is not bad. It's based on the acidity of these carbonyls. Oh, fine. Aldol condensation. So once you're done aldol addition, you could yeah, do this thing. This will create a stable pi conjugation thing. That's good. And in acidic medium, you can also do this. So aldol reactions are usually done with 2 units of the same aldehyde. When it is done with different aldehydes, cross aldol reaction, the percentage is reduced to side reaction. Okay, cool. Canizaro. There's a lot of rate calculations and stuff. You don't need to understand all that stuff. So it's just OH minus entering inside this carbonyl, creating a lot of negative charge density, and essentially hydride shifts occurring from molecule to molecule, like very similar to how ALH4 works. So it collides into something, and while colliding it transfers hydride. So it's the same thing over here. It too transfers hydride. Okay, that's fine. What is this reaction? Anhydride formation, of course. Then yes, this thing. So acid plus PCl3, that gives us acid halide. All right. But acid, or it was like something else. It was ketone plus PCl5 that gave us geminal dihalide. So, yeah. Amide creation. Low temperatures, it will just do acid base reaction. At high temperatures it will do this thing, decarboxylation and decarbonation. Fine. I mean, okay, this is a reversible reaction. So, of course, you need to remove water in order to actually do this reaction. That is. Soda-lime decarbonation of this guy. You will see this in Friedel-Crafts, Yeah. When you try to acylate using tert butyl COCl, you won't be able to do it. Instead, you will get an alkylation because it just doesn't do it, of course. HVZ reactions. Okay, not bad. So it's a way to what? Halogenate acids. So what you mean is like acids can't be halogenated right away? Huh. Of course they can be. Because if you know the mechanism, it basically relies on the acidity of the carbonyls. And in this case, the acidic hydrogen is this hydrogen, not the hydrogen attached to this carbon. Which means, yeah, we need this actually. Right. Disulfuric, not in syllabus, don't even look at it. Wittig reaction, we just saw this somewhere. Okay, fine, whatever. Imine hydrogen, okay, formation. Okay, fine. So like aminolysis, if you want to consider that. Oh, yeah. Okay, Wolf-Kishner, whatever, reduction. So using hydrazone. Wait, no, hydrazone is this thing. What's this called? I don't know. Yeah, whatever that thing is. Okay. Yeah, isn't that bad, honestly. So it is same thing, just remove oxygen and put 2 hydrogens instead. Fine. That's Wolff-Kishner reaction. Okay, cool. Still, just go through the mechanism once more. So first you need to form an hydrazone. Yeah. Then you need to do this kind of resonance, creating this thing. So our aim is basically to form N2 molecules over there and then make it leave. And once it leaves, it is irreversible, and that's why this reaction will be driven forward. ROH plus Na. Yeah, this is obvious. Not bad. ROH plus RX plus Na, well, that's a different thing because that will create NaX plus ROR. So yeah, Lucas test. Right, cool. ROH plus PX3 gives, so ROH plus PX3 gives RX, and alcohol gives halide, but acid gives acid halide. PCC oxidation. Fine. Actually, yeah, it's not bad. Next, you got this reaction. So I just told you that when you got ROH plus Rx in sodium metal, that will give you ROR plus NaX. You can also use this ether thing that you got and treat it with HX to give this thing. If you treat it with H2SO4, then you will get two alcohols basically. So it's ether hydrolysis. Ether hydrolysis is not so common because ethers are much more stable, right? Victor Meyer test. These things are important, all right? So RCH2H, primary alcohol, you iodide. Okay, fine. You halogenate this thing, then AgNO2. AgNO2. Yes, AgI precipitates. So yeah, form a nitroalkane from that. So in all three reactions, you are going to form a nitroalkane this way. Then you treat it with HNO2, NaNO2 plus HCl. Okay, NaNO2 plus HCl. That's weird. Okay, cool. I don't know what the mechanism of this step, but if it's saying that this works, well, then that works. Okay, so it's oxidation basically. Depending on the number of hydrogens, it does it differently. So you form nitrolic acid or pseudonitrile, or it's no reaction at all. And then with KOH, it gives different colors. Okay, fine. That's weird. So that's Victor Meyer test. It's used to differentiate between 1, 2, and 3 degree alcohols. Alright. Pinacol reaction. So this rearrangement, yeah, it can create a more stable product, and that's why it happens. Periodic oxidation, it's weird basically. I mean, iodine at +7 oxidation state, right? That's if it's not weird, then what even is it? So it does something like that. So the main step is this thing, that from here you go to this, and from there you break some stuff. So you break one of the oxygen carbon bonds, and at that point you also form one of the oxygen. So you actually like completely destroy the carbon bond as well. Okay, that's weird. You are not destroying oxygen carbon bond, you're destroying carbon bond and oxygen iodine bonds. I get it. So that's one way of iodine to basically lose its oxidation state. So now the oxidation state over here for iodine is just 5, while over here it was 7, and it oxidized carbon. Cool. Dakin or Dakin reaction. Yeah. So this is only phenyl shift is very easy. So you should actually look up the actual mechanism for phenyl shift, because it's not exactly like a like high drive shift or alkyl shift over there. No. Instead, it's more of a walk instead of a jump, if you know. So first phenyl attacks and then it leaves. Not that it first leaves and attacks, or it does both at the same time. No. it will first attack and then it will leave. Cool. Ether and alcohol explosion in air. Okay, not bad. Dehydration. That's Benedict's test. Okay, cool. Same as Felling's test, but with copper citrate. Hey, okay, so in Felling's test, it was not copper citrate but copper tartrate. Okay, that should make sense. Fine. Shiver's test, same as Felling's test. Okay, cool. Shiver's and Benedict's. Fine. Coricum oxidation. That's complicated. Okay, fine. So from here to that step, actually you use the tetravalency of sulfur. So you make oxygen attach over there and then do a proton shift, and that does it. Okay, fine. And then some good base will come in and then take this out. Okay, that's complicated. So it's something like an elimination. Fine. Why did I just show elimination directly? Does it have to be in a cyclic state? Yeah, I don't know. Okay, fine. That's Coricum oxidation. Okay, next. Fatty zone oxidation. Yes, this thing. So Ag2CO3 solid. It does two things. First of all, the silver that goes from Ag plus to Ag0, that is silver metal, and in doing that it creates positive charge and basically creates protons on that guy, our alcohol, and those protons, well, they go to this CO3 2 minus ion and then create H2CO3 basically, and H2CO3 on heating that converts to CO2 gas, which leaves, and since it leaves it can drive this reaction forward, I guess. Yeah, and that looks about right. Okay, that's fine, not problematic at all. That's fatty zone oxidation. Okay, then here you got ketone plus peroxy acid. We already got what happens with alkene plus peroxy acid. It just gives epoxide, but with this case they're a different thing. Yeah, you get this thing. Isn't that weird for some reason? Like, yeah. Oh, this shift over here, this R1 shifting to a different oxygen, you'll see once more at some point in this. So this shift is not that uncommon actually. It can happen if it gives us a good stability thing. So yeah, and considering that you had a peroxide bond at first, this is actually going to happen obviously. Okay, that's fine. So it creates two acids, one from the peroxy acid and one from the uh for from this thing. Okay, cool. Now I don't know which one of these R1 and R2 should leave. How do you decide that? Well, I guess whichever one has like uh more negative charge. Like, no, that's not right. Whatever. Okay, this is the second time I've seen this. Once again, second time that I'm seeing. Okay, this is different. This is not with alkene, this is with ketone. Wow, what is this? It's complicated. So you got this ketone, you analyze this, then you make it attack SeO2, forming this thing. Huh. Okay. I mean, okay, it's not bad. It adds like what CrO3 would do. So it adds like CrO3, it just adds like that. Then H2O. Okay. Wait. First of all, first before H2O, you have this elimination step over there. Okay, that's weird. So you can do that. You can eliminate this. Wow. Fine. And then H2O over there. And that's how you get this ketone. So after hydrolysis, you will get that. Fine. Once again, another elimination step. Okay, cool. So this is how it happens. Fine. Babler oxidation. Okay, cool. This is an allylic alcohol. Okay, cool. So yeah, till that part it's not bad, but then this shifts in a weird way, so it attacks that. Oh shit, this should not happen. So it attacks that, and then it shifts like this. So it can only do 1-3 shifts, I guess, and that creates this thing. This. Okay. Fine. I mean, this cyclic transition is not that bad. It's not hard to imagine. This looks like a legit mechanism. Okay, SOCl2 on alcohol. Wow, lot of different mechanisms. So if you got SOCl2 without anything, well, then it will just do SNI, I guess. Okay. SNI, huh? So it's in a single concerted step like that. Wow, weird. Okay, fine. So it does that in a single concerted step and it creates an I product which is having retention. If you do it with HCl, oh yeah, I mean, okay, HCl just adds it. Okay, it just adds with it like that. Yeah. There's also something like tosyl group that can attach on oxygen and make it a good leaving group? Yeah, I forgot about that. I guess it works the same as that it can make it a good leaving group because of resonance. Okay, that's cool. But according to that, using transesterification, we can also use, say, something like a carboxylic acid, and that would also make it a good leaving group. Yeah, of course. That definitely can happen. Like, okay, why not just use halo acid by itself? That's the best thing, right? So just using halo acid by itself, that will give us this guy. Okay, cool. Using this kind of compound, I don't know what this compound is. It creates this. Okay, so it's like 2SN2 over there, and that is not SNI. SNI is not 2SN2s, it's a single concerted step. And you also got this with pyridine. With pyridine, it will go through inversion, so just a single SN2 over there. Oh, look at that, that's such a good leaving group. It begs for electron density. Okay. Yes, this thing. So dithiene, when added, make this hydrogen acidic. So when you put BuLi over there, it creates this master cell anion, and yeah, that changes the site at which nucleophile would attack, basically. Oh, okay, wait. No, it changes the site where an electrophile would attack. Normally, electrophile would attack at the oxygen, but in this case, it's attacking over here at the carbon. And this dithiene is also used for something like protection of some groups, and it can be removed with HgO. Okay, fine. So you can form a lot of stuff from that. Okay, then deproduction of dithiene, exactly, that's what I was talking about. So HgCl2, that's the longest mechanism. So essentially what happened is that you just used it as, like, say, H plus, so it is attached to sulfur, then this sulfur kicks that, forming this guy, and then you got hydrolysis basically doing this guy. Once again hydrolysis. Wait, not hydrolysis, what is this? Chlorine. Wait, just what? Okay, so it formed this ring. Oh, okay, fine. So it forms a good leaving group by itself. So is sulfur carbon bond harder to break? Is it stronger than carbon oxygen? That could be. That maybe, just maybe, carbon sulfur bond is like stronger or something like that. Could be, right? But then you got a lot of H2O, so it should be happening by itself, and I don't know. Then this reaction, it's similar to Deccan reaction, except that you have a hydride shift over there. So the reason why it happens is that in this case you have this OH group attached over there. So it's like when you will try to put the mechanism together, the phenyl shift mechanism, you will realize that it's putting a positive charge on these carbons, this carbon, that carbon, and this carbon, right, which cannot be reached by oxygen's lone pair, right, and they are still subject to the negative inductive effect that oxygen puts. So that's bad, that's just bad basically. Yeah. Yeah, that looks correct. Fine. That should be creating this kind. Yeah, man, what could go wrong over there? This should be looking correct. Fine, so it just happens. I don't know why, but like you got a hydride shift over there, and same thing happens with NO2 as well. And these some facts, not so important. One OH is called monohydrate, 2OH dihydrate, so on. Allylic alcohol is this thing. You know all that stuff already. Okay, cool. So that was carbonyls. Yeah, you wanna go to amines, I guess. Reduction. LAH will reduce to just 1 mole of of LAH will reduce 1 mole of amide to an amine, and RC12 bond and H2NI. That will also do this thing. Okay, cool. Okay, that's also fine, not bad. And NH3 plus RX. Yeah, this thing. So iodine, carbon iodine bond is the weakest, and that's why it's going in that way. Fine. Gabriel phthalimide synthesis. So this is phthalimide, and then there's something called phthalic anhydride, where there's oxygen instead of nitrogen, right? So it's formed from phthalic acid when you heat it to dehydrate it. And it's weird because generally acid anhydrides are very unstable, and like, yeah, they decompose when you put H2O inside it. But for some reason, these phthalic anhydrides are stable. Like, these can be isolated very easily. Yeah, so these are used in a lot of different things. This can be used to create phenolphthalein. So the phthalate part in phenolphthalein, that's from this phthalic anhydride or phthalic acid. Okay, so phthalimide plus KOH, that does this thing. Obviously it's a good base because resonance and all that stuff. So yeah, it's a good base. Sorry, it's a good acid. I mean, okay, phthalimide is a good acid, and yeah. And then what? And then this thing, and then this thing, SNAC. Fine. I mean, it's fine. Okay, this looks fine. I always wondered, why doesn't this thing enolize, or do something similar to enolization, and then that will create something like an aromatic system, right? Why doesn't it do that? But if it doesn't, if it doesn't, it just doesn't, right? Yeah, and that's not even important, so why even worry about that? Okay, that's cool. And NH2 and H2 does the same thing, except that it acts like that without breaking that NH2 NH2 bond. Okay, fine. Hoffman-Romaine degradation. This is important. This is very important. So when you install this bromine group by this process, this bromine group will later be very important in the whole process. So what you do now is, where did it go? Yeah, over here. This is the step. Fine. So you got this bromine group involved over there, and then it does this thing. And now the next step is important. These yellow arrows, that's what is going to happen in the next step, that the oxygen lone pair goes down, but it kicks off R minus instead of anything else, and that R minus goes to the nitrogen, kicking out this bromine. Weird, right? But that's what happens. And this, after this rearrangement, you have this kind of complicated looking product. It's not a product, it's still an intermediate, but yeah, you have this thing, and then you hydrolyze this thing to create an acid, and then you heat it. Yeah, basically, well, it's not exactly an acid in the first place because it's got complicated stuff going on over there, right? And then you heat it and it loses the CO2. It's very similar to say H2CO3, if you like. Yeah, it looks like that more than anything. So it's got 3 oxygens attached to it, which is not good. It's not so stable, and that's why it will, okay, not 3 oxygens, 2 oxygens, 1 nitrogen, but you get it, right? This is unstable and it will convert to this thing, carbon dioxide and RNH2. Basic strength of amines: alkyl amine, then NH3, then aryl amine. Guess why is that? Because in aryl amines, the lone pairs, well, they are in resonance, so resonance stabilizes the whole thing, but in that case, when you put H plus on that lone pair, it cannot do resonance anymore, so your resonance energy, well, that will decrease, and that's not good. That's why aryl amines are low, even though, like, yeah, whatever. Fine, so cool. And also because, like, sp2 carbon is not good, so but the main reason is just the resonance stabilization of the basic form and not the conjugate form. Then NH3 itself is okay, and alkyl amines, well, those can give you electron density, so that's good. It's not about hyperconjugation really in alkyl amines. It's just that alkyl amines just give you electron density inductively. Really, that's what happens. So bulky groups in 3-degree amine decrease the strength because they restrict the sp3 hybridization of nitrogen, so it's not exactly able to completely be in that state, in the structure where it can accept hydrogen like that, so it decreases the strength. Groups that resonance stabilize the amine, not in ordinary form, as we saw in the first one. Positive inductive, okay, this is obviously well known. Hydrogen bonding with solvent increases the strength. The basic strength, I don't know about that, but if you say so, fine, I'll consider that. Bridgehead nitrogen has good strength because no amine flipping. That's important. I just told you that these bulky 3-degree groups, those decrease strength, and I told you the reason is because they don't allow the full sp3 hybridization, because that will put a lot of repulsion between the bulky groups. So they do something like something between sp3 and sp2, and that's why those lone pairs are not fully developed to capture that H plus. And similarly, there's amine inversion going on every time, so it's continuously converting from sp2 to sp3, then sp2 to sp3, so on. So because of that your basic character is low, but when you have a bridgehead nitrogen, well, it cannot do that thing. It cannot do amine inversion, and that's why it has a very strong basic character. In aqueous phase, ED2NH. So this you have to remember. Okay, I won't spend time on memorizing this thing. Fine. Reactions. This is well known. Okay. Acylation. So first acylate this thing, and then what? Why do you acylate it? Okay, whatever. Acylation more like formation of an amide. Yeah, fine. Carbylamine reaction, isocyanate test. This is important because it's asked a lot. So it's not exactly this carbene directly, but it's halo form and OH minus that will form this Remar-Teman type, Remar-Temar, whatever that thing is called, type carbene, and that will do this thing. Yeah, from an isocyanide. So with phenol it forms something like and what was it an aldehyde. Yeah, it formed an aldehyde, and with this it forms this isocyanide, right? It's weird. Whatever. Next, Hinsberg's reaction. Okay, what is this? Rock is insoluble in water except when R2 equals to H. Okay, so what you're saying is that if this amine is 2 degree, then this product will be insoluble. If this amine is just 1 degree, then this product will be soluble. Okay, if it's 2 degree, the product will be insoluble. If it's 1 degree, it will be soluble. Not bad. And yeah, looks like a straightforward reaction, so not bad at all. Diazonium salt. Okay, I'm not gonna do this. Not this thing. Okay, pulse Shaman reaction. These are complicated because the mechanism is not known. So all you need to know is that whatever negative anion, okay, whatever this anion is, it will just add to AR plus. Yeah, essentially that's what's happening. So we got this thing ARF plus BF3. Okay, so during SN1 we have a highly stable AR plus ion. If copper powder is used as a catalyst and Diazonium salt is prepared in C2, then we get ArNO2. Okay, fine. Diazonium coupling, well known. H3PO2 reduction. This is weird. So yeah, this happens in fact, even though it's weird. Cool. So it's going by radical mechanism. I don't really care because all we need to know is the products. ETOH reduction, the same thing. It just gives this hydrogen to it and becomes this thing. It gets oxidized by itself. Yeah. Okay, so that's amines. Let's go to phenols and anisole. Looks good. Okay, some common names. So this is cresol with 1 OH and 1 methyl group. Then it's catechol, resorcinol, quinol with OH groups, 2 OH groups that is. Then salicylic acid, salicylaldehyde would just be the aldehyde of that acid. This is acetyl salicylic acid or aspirin. Aspirin is an analgesic, by the way. Okay, preparation of phenol. Yeah, the usual phenol from pH SO3H. We just saw that in that aromatic thing. Okay, pH and 2x plus H2O. That's just such a costly thing to do, but whatever. Quinine process. That's the actual way that this is prepared. So yeah, cool. So this is not bad at all. Quinine process. It does this thing, and yeah, fine. It's complicated and very long, but you know, in the end, it's just the reactants and the products that matter, and the conditions. Reactions of phenol, Friedel-Crafts reaction. Okay. When we add a catalyst in excess and heat at high temperatures, we are essentially doing Fry's rearrangement and not Friedel-Crafts directly, by the way. Okay, reaction with X2 or with or without catalyst. Well, if we add catalyst, that's bad. It will hinder the rate, so better we just not do it. So yeah, you can do it with or without catalyst. Kolbe's reaction. So you might say, why can't it just do you know, like, why can't it just react in the Friedel-Crafts reaction with or without catalyst? That even if you add catalyst, the catalyst got attached to oxygen. Well, that's okay as long as you can just react with it by brute force, right? When that catalyst attaches itself to oxygen, that hinders the rate, because oxygen cannot now use its lone pair anymore. So yeah, problematic, very problematic. Okay, cool. Where was I? It doesn't do ARSN even under acidic conditions. Yeah, cool. Kolbe's reaction. So it's with CO2 and you got OH minus over there. So it forms picric acid like that. And what else? Just wait a second. Okay, Kolbe's. Fine. Oh, that's something new. So it can do that. This is benzoquinone. Weird. That's also another weird reaction. So PHOH plus zinc. I wonder how it does that. Maybe it's like by this might be just a wild guess, but something like single electron transfer to one of the alkene bonds, and once that happened, it will yeah, it could do that, you know. It's possible after all. Sure, it's possible. And then there will be like a hydride shift, and then it will it's just too complicated at that point. It has to remove that OH somehow, and that must go by an E1 reaction. Yeah, is that right? It's not a negative charge in that case, right? But how do you reduce alcohols with zinc dust? Did we even see that mechanism? We saw for carbonyls. I don't remember for alcohols. Uh, yeah, whatever. Next, Raymer-Thémard reactions. We have seen a lot of these things till now. Lieberman nitroso test. This is important. So you first nitrosovate the phenol, and then you form this quinoxime thing, and then you do it with the phenol. You do coupling, and you create indophenol, which is red, and in NaOH it is blue. Cool. Okay, fine. Yeah, sure, this is right. Okay. Ceric ammonium nitrate, CAN. So you use ceric ammonium nitrate with phenol to complexate the phenol like that, which forms a greenish precipitate. So your solution goes from orange red to now colorless with a greenish precipitate. That's CAN test for you. Okay, FeCl3 test for phenol derivatives. This will form violet. Okay, cool. Reactions of any sol. Cool. So the main thing is like Lieberman nitroso test, that's something important. And you got ceric ammonium nitrate test and FeCl3 test. FeCl3 test is the easiest to remember. It's just straight away like phenol completely, I should say phenolate, completely removing all the chlorines over there and forming this violet complex. Ceric ammonium nitrate test is a little different. I guess this thing is not just for phenols but for generic alcohols, but for phenols it is with phenolate ions. For alcohols it's not with ions, it's just normal alcohols coordinated by lone pairs and d orbitals accepting electrons and stuff. Yeah, that's for normal alcohols. And Lieberman nitroso test, this is just for phenols, of course. Also for basically for nitrophenols, I should say. So yeah, so you could also use this as a test for nitroso group, right? So nitroso could be added to this phenol thing and then do all the same stuff, and if there was nitroso it would show this reaction, otherwise it won't, and stuff like that. So yeah, it's fine. Okay, so we got this done as well. Next, let's go for tests for functional groups. Bayer's test. This KMNO4 is called Bayer's reagent, and it does this thing: purple to no color. Bromine water test. Br2 water is yellow. Yeah, it brominates the thing. Cool. So its yellow color diminishes as we go on. There's also the haloform test where this yellow color completely diminishes from the solution and you get yellow precipitate, or I should say yellow crystals of haloform, right? That's the haloform test. Actually that's not yellow for bromine, it's like iodine, right? That's iodoform test. It's different, but you get it. A similar thing happens with that as well. Lucas test. So it's the rate that you have to look at, and this rate is basically given by forming an oily layer, because RCl is not Protec anymore, so it cannot mix that well with ROH, or sorry, not ROH, it's H2O, right? Yeah, You cannot mix that well with H2O anymore. So it forms this thing. While ROH, it can mix. So if there is reaction, you will get a lot of oily layer. If there's no reaction or slow reaction, you won't get that oily layer. So that height of oily layer, that will tell you about the reaction. So yeah, so looking at the mechanism, you can clearly see that 1 degree will give a slow reaction and 3 degree will give a fast reaction, and 2 degree somewhere in between. CAN test is not just for phenolates, it's for any alcohol. Then iodoform test, it forms yellow crystals that go down, it's precipitate. Yeah, it's like not bad. You can use different reagents to create iodoform. So you can not iodoform, the conditions for that iodoform reaction. So basically I2 and OH minus. So you can use NaOCl, Ki, and H2O. Cool. So it's like ICl basically. It's not I2, but it's fine. Not a bad thing. Because I2 would be even worse. You need to like remove that HI in that case. So it's better if you just use ICl. Then you got, what's this thing? Yes, the FeCl3 test. So we already saw that phenolates that give us a violet color, but you could also use some other compounds. So you can use resorcinol, naphthol. Those will give different characteristic colors. So resorcinol, OM or P, cresol, they will give violet or blue color. Hey, by the way, what was resorcinol once again? Was it ortho, para or meta? Meta was, I think it was like catechol. Para was hydroquinone, and ortho was resorcinol. Let's just look at that once again. Okay, that's gone. We'll look at it later. Yeah, and then with naphthol. So naphthol is basically naphthalene with an OH group. So that gives no characteristic color. Fine. Wait, isn't that naphthanol? What's naphthol in that case? Should be the same thing, right? Whatever. Phenolphthalein dye test, as I told you, the phenolphthalein part comes from the phthalic acid. So it forms phthalic anhydride, and then this phthalic anhydride with PHOH, it creates this compound that gives a dark pink color with NaOH, which is basically phenolphthalein. So different compounds, when you use instead of phenol, you get different colors doing this whole process. So O-cresol gives you red color, M-cresol gives you purple. Cresol is for 1 methane and 1 OH group, and cresol, all these catechol, resorcinol things, these are for 2 OH, right? Okay, we will look that up once again. DNP test, this thing. So this is the DNP molecule that with ketone gives this thing. Okay, fine. But what about this test? How do you distinguish anything from it? Okay, so just a normal test for carbonyl. If the reaction happens, it's good. Not, then that means there's no carbonyl. Fine. Shifts or or whatever this thing is, test. Okay, this is too big. I'm not going to remember this one. Main thing is that aldehydes will do this. Yeah, looks like that. So aldehydes will do this, ketones won't. So it goes from colorless to being colored. Cool. Ester test. Yeah, there's nothing special about this thing. Oh, so the main thing is that um, this carboxylic acid, when you put it in NaOH, it can give you this salt or whatever it is. Will it be a salt? I think it's a salt, right? I mean, okay, it's definitely salt, but will it like precipitate? No, it won't precipitate. No, that's not correct. Whatever. The main thing is that will give you this salt, and ester won't give you a salt when you put it in NaOH, right? At least it won't readily give you a salt. It will basically like hydrolyze this thing if you do that. Okay, carbylamine test. We've seen this 2 times till now, so we know it. Then there's azo-dye test. So butanepthenol plus a diazonium salt, that gives a coupling reaction, which is an azo-dye, which is red. Fine. Fellings and Benedict's test, we just saw the mechanism and everything. We have done this, of course. So tolerance test is also called silver mirror test because it deposits like Ag metal on the test tube, so it forms a silver mirror. That's nice. We just need to check what resorcinol and all that stuff was, right? So let's go top. This thing is catechol. Okay, so ortho is catechol, meta is resorcinol, and para was hydroquinone or quinol. Fine. Ortho is catechol, meta resorcinol, para hydroquinone or quinol. Fine. Let's look at what else do you have. Polymers. Okay, let's do that as well. Polythene, benzoyl peroxide, radical initiator. That's what I was talking about. Low density and high density chains and all that. This is styrene. Okay. This is too much. It's not going to be any useful if I keep talking about it. So yeah, we won't do it. What else do you have? You have chemistry in everyday life. This is also something that involves a lot of memorization, and it's basically not even exactly JE stuff. It's like it's a lot of biology and things over there. I don't want to get into pharmacy, so this also needs so much of memorization. But yeah, and by the way, this answer is actually this collection of all these compounds, it's not mine, it's from some Quora answer. Yeah, I edited a little bit of it, the corrections that he basically said should be done, so like these, whatever. So you guys can just pause and take screenshots of this because this might be important. So this is the first page, and then there's the second page. See, then okay, so that's for this one. And what else is remaining? That's it. That's all there was to all the organic chemistry notes that I have done till now. That was short. I thought that will take more time, but yeah. So that's right. I'll see you guys later.